This
Okay.
meeting is being recorded.
Okay. Um, all right. So yeah, I'm Alexandros. Thank you for inviting me to speak here. It's nice that you're organizing the seminar. And today I would like to talk to you about Jackiw-Teitelboim gravity and its relation um, to hyperbolic geometry and matrix models. So uh, let me start with a little sketch. So we have two-dimensional gravity, which in our setting will be this JT gravity, which I will explain what it is. And we want to see its interplay with matrix models and some nice mathematics, specifically hyperbolic geometry. Okay. And in this talk, so I will mostly concentrate on this part. So mostly the JT gravity and a little bit of the others. Maybe a little bit more matrix models, so I will try to explain also what that is if you haven't heard about them. And the main topic is to uh, describe a duality uh, that was discovered by Shad, Sankar, and Stanford between this JT gravity, which we will say what it is, and a specific matrix model. So this was by Saad, Schenker, and Stanford in 19. And we also have some work with it relating to the subject with my supervisor Hans Jokers and some collaborators from Bonn, Stefan Forste and Joshua Kames-King. And I will try towards the end to talk a little bit about our research as well. So the nice thing about this story here is that it incorporates novel results. So very important results in mathematics, as I said, specifically the work by Mirza Kani. So she was a mathematician that earned the Fields Medal, uh, and by Einard and Orantin on. So I will write here. It's called topological recursion, but in our case, it's matrix model. Okay, so this whole story is it was very much based on works by these people as well. So uh, let me first say what is JT gravity and some brief history. Okay, so this is going to be a two-dimensional setting, uh, and in 2D, so 2 dimensions. Uh, you might have seen that the Einstein tensor vanishes identically, so it's zero for any metric. So this means that there's on the classical level there is a problem with formulating GR. So general relativity uh, can be formulated at least as we know. I mean, the regular Einstein-Hilbert term is a total derivative, so it gives you no dynamics. Okay, so that on the classical level. Okay, so the Einstein-Hilbert term is a boundary term. Okay, and so now Jackiw and Teitelboim, so independently but not together, around the 1980s, they propose that the dynamics are governed by a different, so by the following equation. So the richest scalar to be minus 2 lambda, where lambda is a constant, in a way to tackle this problem. And why this? So some motives for this equation, it's that it's a second derivative and geometrical equation, which is what we like. And it's also analogous to what you would get. So this is a bit sketchy, but analogous to 3D. So if you go to 3-dimensional and you do Einstein-Hilbert plus a cosmological constant, you would get something like R alpha mu beta nu equals minus lambda 3 mu. Okay, so analogous in the sense that, well, they're not the same, but you have on the one hand side something dependent on the Ricci tensor, on the right hand side the cosmological constant. So that's just as a motive. And another motive for JT gravity now is, sorry, before that, this equation right here can be derived by an action, because we usually work with action. So an action for this would be the following. So you have the action is minus 1/2 integral. So you integrate over your manifold. So remember, this is 2-dimensional, and this is always going to be Euclidean signature. And now the thing is that, so here I put lambda equals 1. The thing is that we also have now a dilaton. The dilaton. Should I answer the questions in the chat now? Yes.
Yes. Yeah.
Okay. Yeah, just you can also talk to me because I might not see it. Yes, the richest scalar is the richest scalar. Yes, R is the richest scalar. So the one we know from general relativity. Yes. All right, and so you see from here that if you vary the action with respect to phi, you get this R plus 2 equals 0. Okay, so that is the Jackiw-Teitelboim action. So it's the prototypical form. So
1 second, you vary, but there is no kinetic term for phi. So phi,
yeah,
it's like a Lagrange multiplier. It's not a dynamical field here.
Yeah, it's like, so this will be important in the next steps. So it's a linear term, so it's like a Lagrange multiplier, yes, as you said. And when you do quantization, it helps you. It makes the story much easier, because it's like imposing a constraint on your manifolds, specifically this R plus 2 equals 0. Yes.
And what happens if you vary the metric?
When you vary the metric, yes, you get some constraints on phi, I think. Yeah. Yes, but phi should not be dynamical, I guess, because there's no kinetic term, so it's you can integrate it out. So yeah, I don't have, so there are equations when you vary the metric, but I don't have them right now. But yes, you can also vary the metric. Yeah. So the idea is that here you want somehow to impose this R equals minus 2 lambda from an action, and the easiest way to do it from something that looks like Einstein-Hilbert is you multiply by this phi. And yeah. Okay, and right. So, and JT, Yes, it's also related to more general dilaton gravity models. And this means it's also related to black hole physics. So what I mean is that there are other also theories with the dilaton, which is the scalar field coupled to Einstein gravity. And in some certain regimes, if you put this in the added de Sitter space, which you cut off at some point, some models can be described universally by this JT. So if you take the limit, you find JT in some cases. And since also some black holes can be described in terms of this dilaton models, JT is also related to this. And yeah, now you might ask, what happens if we change this a little bit? So you could look at deformations of JT, and I would like to come to this also later. So by deformations of JT, we mean adding some extra terms to this action. So in general, you can write it like this. So we have phi r plus some general potential W of phi, with W of phi equals to phi plus some U. And you see now, if I put U phi equals to 0, I get I. So I get this here. Okay, and some interesting deformations, which we will say later why they're interesting, is if you put U equals to 2 epsilon e to the minus alpha phi, and then alpha is in phi comma to phi. Okay. Yeah, this deformation and its quantization were studied by Wheaton and also Maxfield, Turiaci, and Mertens. Okay. And now I would like to move on to sketch how one goes about calculating the functional integral of JT. Okay. All right. So this will be the procedure by Sal, Schenker, Stanford. Oops. Okay. So now we have JT. We showed what's the action, and so now we're going to give a bit more of a larger action. So we would like to calculate the functional integral of the following. So I will explain. We have some constant S0, and then first comes some piece of the action which is topological, which means that it does not depend on the. It just depends on the topology of your surface. So this part is topological. Okay, then this is simply the Gauss-Bonnet theorem, and it will give us a weight depending on the genus of the surface. So specifically, so this is a number, which is called the Euler characteristic, and it's equal to 2 minus 2g minus n, and g is the genus. Genus is the number of handles your surface has as n, and n is the number of boundaries. So for example, if I draw something like that, this has g equals 1 and n equals 2. And then I have minus 1/2. Now I have the JT action that we talked about. Okay. plus phi. And now there's a boundary. So this is a boundary term. Okay. And this sorry, here this is k. This k is called the trace of the extrinsic curvature. There's an explicit form. It's not so important right now. So we have these three terms. The first term, as I said, is a number, and this will just give a number in front of the functional integral that will depend on the surface that you put your theory on. And now what one would like to compute is, so we want to integrate. So what are the fields that you have here is the phi and the metric, and we want to integrate over the geometry, and this is, I write it in a very general way, so I mean the metrics, and we want to integrate over the field phi of this e to the minus ijt. And there are also some boundary conditions which I will state, but I don't want to focus on this. But so, what are the boundary conditions? Boundary conditions. So you want your manifold to be orientable and have n asymptotic boundaries. So if I have this thing, for example, will have one asymptotic boundary, so it's like very far distance, and you can imagine by something like cutting it off at some to regularize it, and the lengths of these boundaries are going to be, so for each boundary I have a constant over epsilon, so, and this epsilon is supposed to go to 0 in the end, and you fix the value of the dilatonic field on the boundary, and you also fix the metric of the boundary. So you have a boundary, a one-dimensional boundary that goes around like a circle, and you fix the metric to be 1 over e squared. So this epsilon goes to 0 in the end.
Sorry, can you go back to the boundary term itself?
Yes.
So why is it k minus 1? Probably you
Yes.
need to show that only this combination of terms is invariant under DFOs. I mean, it's a general, it's a different
one,
version
right?
of the Gibbons-Hawking term, I guess, because you have phi in front.
Yeah, yeah. It's the Gibbons-Hawkins York term, and this minus 1, it's there to cancel some divergences. So when you impose this constraint and you calculate what is this k, k is something like where this is a normal vector. You will find some terms that go 1 over epsilon squared or 1 over epsilon, I don't remember. But when you have, yeah, so this minus 1 is there to regularize stuff, so to cancel some divergences.
Okay. But I still don't see how phi gets a boundary value if it's not dynamical. I mean,
it's a boundary condition. So we want to integrate over all possible values of phi. So we're going to integrate it out. So, and that means that we integrate over all of its possible values. Yeah.
But it doesn't have an equation of motion. So.
Yes, but so when we calculate this functional integral, we should impose boundary conditions on the fields, and that's I guess a choice that you can make. And yeah,
let me rephrase. If there's no kinetic term for phi, why do you integrate in the path integral over phi to d phi?
Because because it's a field of our action. So when we do the functional integral, we want to integrate over all possible values, even if they are auxiliary in a sense. Yeah. If so, you see this, it's in a linear term, and so indeed is like a, it's like a, we give a constraint, so it's like an auxiliary field, but still we should integrate over all these values in order to get this constraint in the functional integral. Yeah.
Okay, let's see. I don't want to interrupt you anymore.
All right. So now this this functional integral. So how this is done? So usually, first you do the functional integral over d phi, and if you do that, this includes such a term, and this gives this constraint. So you do this functional integral, and it tells you that everything else. So when you integrate over the metrics after that, you have to do it while keeping this constraint true. Okay, and usually how this is done is you rotate this phi to I phi, and this looks like the argument is that this is like a delta distribution in a functional sense, and because when you get this I phi here, it looks like like you have the integral over a to the I something, and then you get a delta. It's in a sense the functional analog of that. And in this way, integrating out phi gives you this constraint, which you have to impose on your integral over the geometry, so over the metrics. Okay, so now how does a generic surface look? So we said that we're going to look at surfaces that are orientable and have n boundaries and a certain number of handles. So generically, you might have something like this. Where here you have a certain number of holes or handles. So this would be n equals 2, so 2 boundaries. So one here, one here. And what the functional integral will do now is you want to integrate over all possible such surfaces. And what I mean is, like, for example, if you have a circle, what part you can have one circle for each possible radius. Okay, that's a very simplistic example, but here these surfaces have some, they're characterized by some parameters, so to say, and when you integrate over all possible such surfaces, you want to integrate over all of this space. It's called the moduli space, and it will tell us how large is the space of possible surfaces. And how this is done, what they do in their paper is they cut, or they do the functional integral in 3 steps. So you can imagine this cartoon here by being made of three parts. I cut out this piece and this piece, and I choose a geodesic here and I cut it. And this is the boundary labeled by beta 1 and beta 2. These betas are related to the boundary conditions that we mentioned earlier. And now this is a hyperbolic surface with 2 boundaries and G handles. Why? Because it has to fulfill this r plus 2 equals 0. Okay, and now this contribution to the functional integral. So when we say I do the functional integral over surfaces with two boundaries, and then I let the number of handles be as many as you want. So you have an expansion actually in the number of handles. This will be something of the form. I will explain what this is. So you have the, and then, so here now you can, I want to show how the relation to hyperbolic geometry and mathematics comes in. So you see now, here we have two geodesics. This has a length B1 and this has a length B2. And these two, they call it trumpet, I guess, because of the shape. This, you can do the functional integral over this boundary, and it gives you this contribution that I call Z trumpet. And then you multiply it by this V. So what this V is, it tells you how large is this space of possible surfaces that you have in the bulk. So when you integrate over all possible metrics, because what you have to do, you see here, the action, this term r plus 2 will be 0 because of the constraint. And we only have something that survives at the boundary. So the action in this bulk here is just, you have e to the just this Euler character. So you're simply integrating over all the possible surfaces. So in the sense, you just get the volume of this space. And this is it's called volume of moduli space. So it's a volume of moduli space of this kind of surfaces. And it's, in a sense, it tells you how large is the space of this possible, of how large is the space of these surfaces, that how large is the space, how, like how, maybe in a sense you can say how many of them can I make that are not equivalent to each other. And then you multiply by the boundary term on the right. And now you glue things back together. And when you glue things back together, you have to integrate over all the possible lengths of this geodesic. So you can glue them with a small geodesic or a large geodesic, and this will give you a different contribution. And yeah, there's also a B here, but so imagine if you glue two things together, you might glue them directly, or you might twist one and then glue, so this B comes from this twisting.
Sorry,
Okay.
Alex, I have a question. I
Yes.
think I got lost a little bit. So the surfaces are our space-time or our space of configurations?
Yeah. So this is this. Yeah, the space-time. This whole surface is the space-time that you put your theory on.
Mm-hmm.
Now you want to integrate over all possible this deformations or possible metrics you put on this space-time. And the way that they do this is to break it in these steps. So you imagine you can first do the integral over the boundary.
Mm-hmm.
So this would be integrating over e to this boundary term. And now you have to integrate over all possible shapes of the boundary, actually.
Mm-hmm.
And then you also then have the integral over this centerpiece, which just counts, in a sense, how many are my possible surfaces of this certain topology. And then you glue everything together. And this integrating over how large is this geodesic here is an artifact of this gluing.
Okay. And as far as I remember, you mentioned that the Einstein equations were calculated in the boundary, right? Or
Uh,
am I wrong?
the Einsteins.
Or not?
What do you mean?
Or not?
Uh,
uh, well,
so
not maybe I misunderstood it. Mhm.
So the boundary has this term, and this term lives only on this asymptotic boundary, on
Mm,
this red here. Yes, and when you put in the specific values that I wrote here, so we know the metric on the boundary, and we know phi on the boundary, and we can actually calculate what this term is, and you would have something like, so you would have something like integral over, so this is actually the boundary shape, and then you have e to the action of the boundary. And this is, you can actually do this. And the nice thing is that this is calculable, this thing here.
okay, thank you.
Sorry, precisely think on this. I think it's a good question. Namely, what is the background here, and where's the dynamics? Is there back reaction, and how can you split? I mean, do you put your theory on some given background? Because it seems that you don't, because you can consider different possibilities for the manifolds, right?
So okay, I have this action, and the metric is a dynamical field. So what the choice that you make, so let's say you can make a choice that I put two boundaries on my
May I
space.
interrupt a little bit? Because
Yes.
I think the space-time manifold is always ADS2, and then you choose different topologies of right, because you have the Ricci scalar is -2,
Yeah.
and negative curvature corresponds to ADS, and specifically here I think you have ADS2, right?
Yes, that's correct. So because of this constraint, okay, right.
Okay,
The metric on the, yeah, it should fulfill this, and but yeah.
Okay, that's good. That's good. So there's a fixed background, but then when you integrate over your metrics, over the geometry, it seems that there's still some freedom, no?
They still obey the r+2 = 0, but they can do it in different ways.
As status is saying, only the topology changes of that. Okay.
Yeah.
Okay.
I think it's like this sum that we do also in string theory, right? Where you have like you sum over all Zinai, Genesis, whatever this is called.
Right. Yeah.
Yeah. So one part is this, and one part is, so you can make a surface with a certain type of a certain number of handles and boundaries that fulfills this constraint, but the metric is not a metric, so there are deformations that will still be fulfilling this r+2, and that's what you're integrating over.
Great. Thank you.
Okay, so
does the module the volume term depend on B1 and B2?
Yes.
Okay, thanks.
B1, B2. All right. So what we have, or what one can calculate is, so this is just a notation. If I put n boundaries, each boundary is labeled by a constant beta I, and now I sum over the topologies, right? For fixed n, so I fix n to be whatever, and then I sum over the possible genus or geni for this fixed number of boundaries. Okay, and so what this means is, for example, if you have these two boundaries, you start with no holes, and then, so this is called the double trumpet in the literature, and then you have, you can imagine that here, okay, this you add one handle, and then you might add another one, and so on. And this exponent right here, it comes from the topological term in the action, which, okay, there's no dynamics indeed. Once you have specified the topology, and by topology I mean the number of handles and boundaries, the value of this term is fixed, and is 2 minus 2g minus n. So you can see the higher the genus, the higher the suppression of these terms. And this z g comma n that I wrote here, these are the integrals of the bulk moduli. Okay, by bulk moduli I mean what we were talking about the possible bulk geometries, and then you have here e to the boundary action that I wrote here. Sorry, yeah, this boundary action here. Okay, so okay, so this is done in yeah.
Sorry, what do you have the left hand side as a bracket expectation value of z? What does this mean?
Yeah, this is notation, so you can, it's not really important, I guess. Later we will have something that usually is denoted by these brackets on the matrix model side, but you can denote it also like g beta 1 beta n. You can denote it by that. It's not like you're inserting something in the functional integral and you calculate this path integral like in QFT. I don't mean this. I don't mean add an insertion to the functional integral. This is a notation. So this means that you have n boundaries and you sum of the topologies in this way.
Thanks.
Okay, so yeah, we saw now that this functional integral is done in a sense in 3 steps. So you can calculate the contribution from integrating over the boundary. You can calculate the contribution that comes from the bulk after we do this cutting, and then you glue things together. Okay, and what is so nice here is that these volumes that I told you, so these volumes, this V, G, N, that depend on the boundaries. So if I cut here, sorry, here, these volumes are studied by the mathematicians, and Mirzakhani derived the recursion relation about them. And so these are in general very difficult to calculate. And by using this recursion, one can indeed calculate step by step these volumes and actually perform calculations. So this is a nice point where results in mathematics assist the results in physics. Yeah, I could say a bit more about this, but I think I'm running low on time. So yeah, I want to, okay. So now let me briefly say because I said there's a duality between this and a matrix model. So we have these quantities calculated, and now I want to tell you how this is related to matrix models. Okay, what is a matrix model? I want to briefly say what it means. So a matrix model is in a sense a very simple gauge theory. You can see it like that. The fields here, they're not really fields, but the fields are matrices with values in the real number. Sorry, no. What? Sorry. They are Hermitian matrices. Okay, so this is just a case, an n by n matrices, n by n, where n is not related to any n here. Just pick. We have matrices of some dimension. Okay, yeah. and they do not depend on any coordinates or any spacetime. They're just matrices. So I have like Mij, and I comma j goes from 1 to n. And now the idea is that you, sorry, yes, the partition function of such a theory, analogously to what we would do in quantum field theory, you would integrate over actually, okay, you would integrate over all possible values of the entries of this matrix. So this dm roughly means that I'm integrating over all over the diagonal values and all over the real parts and the imaginary parts of the imaginary parts of this matrix. Okay. So it looks very simple, but it can get complicated. So an example would be that, for example, v of m is trace of m squared. So this would be like the analogous term of a kinetic term, but there's no time or space here. So it's a quadratic term plus some potential. Yeah, I should have called this v, but okay. So for example,
is this finite integral?
It's finite. You mean finite?
I mean, if there are no dynamics on them, then you simply integrate over all the values of the entries.
Yes.
Okay.
Yes, you can. Yeah, but you see the number of these are n, capital N, but and you integrate. So over what values you integrate? I think this can be tricky. Sometimes you can choose contours.
Not the values. The measure is a finite product. Right?
Yes. Yes. Yeah. Okay, and you see that so this trace, you need a number out of this to take the exponential. So usually, I mean, what gives you a number when you from a matrix is that you can take the trace, and for example, you can have a potential that looks like m to the fourth, the trace of that, and you see now that there's a symmetry in the sense that I can make if I make a similarity transformation in this trace, it doesn't matter. And this is actually a way that you can calculate these integrals. If they are Hermitian, you can diagonalize them and you can translate this integral over the entries into an integral over eigenvalues. Okay, so now I would write something with brackets. So an observable will look something like we know perhaps from QFT. So this n here. So there are also some conventions which, yeah, you might not always see this n here. Okay, and this f of m usually is a function of m, where m is the matrix that is usually invariant under the similarity transformation, because you want what you integrate here to be invariant under the similarity and also the measure. So when you do the similarity transformation, you can simply have eigenvalue integrals over eigenvalues everywhere. And okay, there's this matrix models. So they also have a genus expansion. So what this means is that, like in QFT, we do diagrams. You can also do diagrams here. But now the matrices, they have two indices. And for example, you can have vertices, but now they look like this. Yes. So now you have double lines. And now to calculate a diagram, usually you pair indices, and pairing indices in different ways gives you something that gives you things that are not topologically the same. And what I mean, so pairing indices, I mean pairing, for example, this with this and this with that to calculate a diagram. If I pair them in a specific way, I might get something like that. But I can pair them in another way, which is a bit difficult to draw. You know, so now this I can draw on a sphere, but if I pair the indices in a different way, you might get something. I don't know if this is clear now. You might pair them in a different way, so you're not able to draw it on a sphere. You have to draw it on a torus. So this does not intersect itself. And this is the 't Hooft double line notation. And now what this tells you is that you can classify your diagrams in terms of the topology of the diagram. So each diagram has a certain topology, meaning on what kind of surface can I draw it on without it intersecting itself. And yeah, so you can classify your perturbative expansion of observables in terms of genus.
So the group tells you what is allowed, right? Because from what I understand, pairing indices means basically forming irreducible representations of the group, of the gauge group, different ones. It's like a tensor product. And so you get a sum of irreducible representations. So the group will tell you which ones you can form. So this tells you which diagrams are allowed, I would suggest, but I don't know.
I'm not sure if it's related to the. So
it's the gauge index you're pairing.
Okay, so you mean if I have MIJ?
IJ are gauge indices, right? That's what you meant. Or
yeah, you can see it in this way, I guess.
Yeah.
But I'm not sure. Okay,
or
maybe
it's
I'm
some
not.
generalist versions.
I thought that okay. I thought that for any. So if I take Hermitian, or if I take symmetric matrices, or if I take something else, then I thought that I didn't know that some topologies are not allowed. Or is that what you're saying? So if I take different kind of matrices, then some.
I'm saying that your starting point, the group you're using, should sort of tell you which diagrams are allowed and which not. Because these are basically pairing indices means matching your external states to irreducible representations of the gauge group you have. If there's a gauge group here, I mean, because maybe it's some generalized matrix model where it doesn't make sense to think of, I don't know, to think of a gauge group.
So here we just. I think it's also related to perhaps more to what interaction, in a sense, you have, what kind of vertices you have, and this is just this m to the fourth. And pairing indices, I mean, what do I mean? When you calculate this thing, you can. I didn't note it down. Remember, like in QFT, where you had this generating function e to the j squared, and then you differentiate with respect to j, and you produce the correlation functions, for example, in the free theory. Here you have a similar thing, but now all of these j's, they have indices. And in order to get, so in the end you put j equals 0, and this j is a matrix. So you differentiate with respect to this j's, and then in the end, if you don't want to get something 0, you should differentiate in a way that the indices match each other. And the possible ways that you match these indices it gives you the different topologies in the expansion. Okay, yeah, I'm not sure if
that's very good. Thank you.
Maybe we're talking about the same thing in a different way. Okay, and yeah, I think I'm running out of time. No?
Well, you can, I mean, in principle, we don't have any boundaries, but roughly it should be around 1 hour. So I would say 10 to 15 minutes more should be okay.
Okay.
And if you need more time, then we can also expand.
Well, I don't want to tire you.
Okay. Yeah.
So what the, okay, this 10 minutes. Okay, now what is, so SSS, what's the procedure I was describing stands on Schenker and, what did I say? Satz, Schenker, and Stanford. What they argued about is that when you calculate this correlation function now in a matrix model, and now this really means something like that, inserting into this integral over the values of the matrices. So if I calculate this on the matrix model, so this means this MM means a matrix model. This matches what we called earlier Z beta 1 all the way to Z beta n. Okay, and these are the connected correlation functions or connected surfaces on the right hand side. And so what I mean here, so there is a genus expansion of this thing in the sense that I described above, a genus expansion of, okay, so there is a subtlety here. This is not exactly like the matrix model I showed here. This is the basic matrix model, but there's also something called double scaled, which is you take a limit where this n, the n that I showed here, the n is the dimension of the matrices. This becomes very large, and you tune this potential that I wrote here in a way that is suitable in this case. So it's a certain limit of the parameters that are in a matrix model, of a Hermitian matrix model. But still is a theory of matrices. So you can also, these are also called random matrix theories. And on this side, you have JT and its own genus expansion. Oops, like this, okay. Yeah, like this, like we argued earlier. And they show that these two things are compatible with each other. So to each term, to its term in the genus expansion matches on both sides. So you have a correspondence. And this correspondence, what I want to stress is that it relied on these results, which I haven't talked about too much, but the results in mathematics by Mirzakhani that I mentioned earlier, who discovered these recursion relations between these volumes that count the parameter space of these bulk geometries. And the works by Einard and Orantin, which what they did is they showed that this recursion relation on the math side is compatible with the recursion relations that are obeyed by matrix models, because matrix models also obey some recursions. So some observables of the matrix model obey recursion relations. So that I think you can think of it as an analog of the word identities. And yeah, they showed that these two are compatible. What compatible means, I will not say right now, but this is the result. And another interesting observation is that you have a bulk gravity theory dual to an ensemble of quantum systems. So I should explain this. So we wrote here something like trace e to the minus beta m. And you can interpret this as, so M is a matrix and you can interpret it as a Hamiltonian, which is random, and the probability distribution of this Hamiltonian as a matrix is this. You see here we have this exponential, so this e to the trace of some potential. So it has some probability density. So it's a theory of random matrices, and if I interpret this matrix as a Hamiltonian, I have an ensemble of random Hamiltonians. So it's like a duality between some bulk gravitational theory to not a quantum system, which would need only one Hamiltonian, like singled out, but something like an ensemble of that. And this is a very interesting observation, and attempts are being made, or examples have been found that, also in higher dimensions, so in 3D, so in 3D you have a similar duality between some bulk, it's called Chern-Simons, it's a gauge theory, and on the boundary you have conformal field theories which are compactified. So the surfaces that you put them on are tori, and this is one part of our research that we're currently looking into. So dualities between conformal field theories, compactified, and 3D bulk gauge theories. And okay, now I have like 5 minutes or less. Maybe. Okay, let me, I don't know, maybe I should stop and we discuss. Or...
Yeah, that's also fine. I mean, if you want to do some conclusive remarks, or we can just stop.
Okay, just I will just say one thing because I mentioned it earlier. Okay, we saw this story, and I mentioned the deformations of JT, and I want to just say that now if you do the same story, but now in the bulk action, you have this deformed JT action that I talked about earlier. So I have something like this, and alpha is in pi comma 2 pi. If you do this, then the constraint that you get is not r plus 2 equals 0, it becomes r plus 2 equals 2 alpha, and a delta function. This is a two-dimensional delta function. And now your surfaces become even more interesting. So you have surfaces with conical singularities, and this means that locally around such points, when you go around this point, the identification is not if you go around 2 pi, but is when you go around 2 pi minus this alpha. And you can, a way to imagine this is if you have a disk or a piece of paper and you cut it here, and then you glue these things together, you get something like a cone, and you develop a singularity here. And fortunately for these values of alpha, these things are still calculable by these recursions that I mentioned. And yeah, so our research, so we had a, so Witten, Maxfield, and Turiachi, so in two different papers, they studied this and they related it also to matrix models. And in our paper, we tried to also study deformations of JT and also these specific ones, and but in another kind of context. So we based on some other works, but I think I should stop here. Yeah, and if there are questions, we can discuss.
Okay, thank you. Good. So, are there any questions?
I have one question.
Okay.
Yeah.
Does the genus tell you something about your theory? Is it relevant, the genus number, or not?
The genus, so it comes in the, you have an expansion in genus. So when you do the functional integral of JT on a certain number of asymptotic boundaries, actually I wrote it, I think, here. So if you have two boundaries, then you sum over the geni, and this is a sum over topologies in a sense. And you see, because of this number you get in front, you get it from the topological term in the action. The higher generi are suppressed.
Okay, thank you.
Yeah.
More questions? I don't see, but if it is okay, I can also ask one.
Okay. Yes.
So I expect that this matrix model you are discussing, there should be a limit that they correspond to some sort of SYK-like physics. Because I know that JT gravity in some limit is dual, it is conjectured to be dual to SYK. And in SYK, you also have a Hamiltonian that has a random coupling between fermions, and then you have a Gaussian distribution, which would mean that you have an ensemble of quantum fermionic systems. So is it known how to relate these matrix models with SYK?
This story I don't know very well, to be honest. I know that SYK is related to JT, but about the SYK I don't know much, to be honest. So I'm not sure if I can answer this.
So maybe I can also rephrase the question. In these matrix models, are they in 0 plus 0 dimensions or 0 plus 1 dimensions?
So these matrix models, they have no, there's no space nor time.
So 0 plus 0, I would guess.
0, yes.
Okay.
Yeah, so that seems different from the usual living on the boundary, right?
Yes, but
I can say something about, so living on the boundary. The matrix model is characterized by a function called the density of eigenstates at genus 0. So what is this? If you calculate the expectation value of, so at each, so if you have a matrix, it has a discrete number of eigenvalues, and if you make it a random matrix, you can ask what is the density of eigenvalues that I would get if I pick a random matrix. And this quantity also has a genus expansion, because it's an observable. And the genus 0 part of that is related to these recursions that the matrix models obey. And if you know this genus 0 part, you can generate all other observables just from that. So in a sense, this density is, so if you don't know, for example, this potential that I mentioned of the matrix model, you can, if you know this density, you can still calculate things. And this density you can read off from the gravity side by calculating the functional integral on the disk topology. And on the disk topology, you only have the contribution from the boundary of the surface, because in the disk there's no bulk moduli. So you only get, sorry, this deformations of the boundary functional integral. And maybe in this sense you can say that from a functional integral over the boundary, you read off the matrix model, and but I agree, it's a bit. So
yeah, I mean, what you draw exactly, well, not exactly, but what you draw is usually used in the Poincaré paths of ADS2, and usually you truncate this boundary, so you don't reach all the way to the boundary, and you have some epsilon distance from the boundary. And in this specific case, and so the JT gravity, when you truncate this disk topology like this is dual to SYK in the low energy limit.
Okay.
But yeah, I cannot. I also cannot see how they could be related right now. But if it is 0 plus 0 dimensional matrix model, then perhaps there could be a limit in which one dimension emerges out of these matrices, and therefore one can also discuss something along these lines. I mean, this would be a wild guess, but
okay.
I mean, if two models are dual to JT, then
yeah, they should have a relation probably with each other.
yes.
Maybe this thing is discussed somewhere, but I'm not sure now. I cannot say something very concrete about this.
Yeah, okay, no, it was just a question of me. So, are there any questions, further questions? If not, then let us thank Alex again for this nice talk.
Okay.
And now I'm gonna stop recording, and then we can discuss if in a more relaxed environment.